Good afternoon, everybody. Welcome to this Institute Colloquium, and we are very happy to have Professor Angshuman Nag from IISER Pune who delivered this Institute Colloquium, which reads as the layered hybrid perovskite. So I request our director, Professor Tanush Gupta, to kindly introduce the speaker.
Good afternoon, everyone. I think you people can, it's already one-sided. I don't know why. Should distribute. So we are very happy to have Angshuman here. I think some of the, members in this family already know Angshuman quite well. So Angshuman did his PhD from IISER Bangalore in SSCU. And even after PhD, you have spent some time there. I was looking at it, and then he was in University of Chicago for some time, and he returned to India as a Ramanujam Fellow in IISER Pune, and since then he has been in IISER Pune, and he is a faculty here now. And today's talk is on this layered hybrid perovskites, and which is a upcoming and fascinating area. And I do hope some of the people who are present in this audience, by motivated by this talk, if not working in this area, will seriously think about getting into this fascinating area. So, Angshuman, the floor is yours.
Hello, am I audible? So, first of all, I thank the committee for giving me an opportunity to share our work here, and it's a sort of kind of big opportunity for me to present a colloquium in SM Bose Center. And from the morning, I've been visiting many of you, and it's been a following experience that I've been going through. And I hope to meet some of you more after the talk. So today I'm talking about layered hybrid perovskite, molecular design and optoelectronics. So it has many keywords. So I expect that at least in the backside there is a diverse background of audience and probably some from chemistry background, though I'm not very much sure of it. So I'll try to give some introduction about first what is semiconductor optoelectronics. Though it sounds a bit weird that a chemist giving introduction of semiconductor to a hall that is mainly occupied by physicists, but essentially I'll try to talk about how we think of when we think of designing new semiconductors. And then I'll introduce this particular material, class of material, that is layered hybrid perovskites, and then show that even in the crystal size can be a centimeter size, the big crystal, and there one can see certain interesting nanoscale phenomena in those kind of big crystal. And then finally, this is the core of the today's discussion. It will be like how we can have some perspective from molecular design perspective of this kind of new semiconductors. We will invoke different kind of non-covalent interactions to get interesting structures. And from those structures, one can get like non-centrosymmetric semiconductor, one can introduce chirality. There is a possibility of introducing molecular intercalation. And then finally, one of the problems in this field is the water instability. We will also address how one can think of those molecular designing aspects to deal with molecular stability of this kind of system, or the water stability of this kind of system. So to start with semiconductor and optoelectronics. So as you know, by optoelectronics, we mean that it involves both light and electricity or electrical current, for example. Say, think of solar cell, light is an input and electrical power is output. So that's an example of optoelectronics. MEB's electrical field is input and output is light. Likewise, you have photodetectors and so on. Now, this kind of properties or applications you get in a class of material that called semiconductors, and not very early. You can see that about 90 years back, Wolfgang Pauli is stating that one should not work on semiconductors. That is a filthy mess. Who knows whether any semiconductor exists? But the things started to change very rapidly, and by late 1940s, we could see already semiconductor materials, their theories, and also some of the devices started to came into the realization, and that happened because of this mighty material that is silicon. Now, one can make this kind of big single crystals of silicons using very kind of demanding reaction conditions like from the melt, like 400, 500 degrees Celsius. One can get these single crystals, and from potato you can get potato wafer or chips like that. From silicon single crystal, you can cut them and you can get silicon wafers or chips like that. An interesting point is there that one can get a purity today, like in the commercially, there is something called 9N kind of purity. There's 99.999%. There are 9 nines are involved here. That kind of purity of silicon you can get commercially very easily. And that is sort of the key thing that changed the semiconductor industry. And here, this is like the electronic band structure. Here you can see energy versus momentum, the schematics, and the silicon has an indirect band gap. Now, when I have an indirect band gap, then the optical transitions across the band gap is forbidden. Now, how come I have a system that is very poor absorber of light, including poor absorber of sunlight, but this works as an extraordinary solar cell material, and if you go outside, most of the places you'll see silicon solar cells are there. So how does it work at all? Now, this becomes possible because of this interesting aspect of silicon, that it is an external good charge transport, and if I put a quantity here, I put the quantity of electron diffusion length. This electron diffusion length more than 100 micrometers, and that is something on the unique aspect of silicon compared to other semiconductors that we see. Now, what does that mean? It means that if I have an electron here, so I can generate the electron, for example, by absorption of sunlight or so. So if I have this electron here, this electron can travel through more than 100 micrometer, and it can reach the electrode or electrical contact and therefore conduct electricity. Unless this electron travels 100 micrometer, it cannot reach from here to this electrode and we cannot collect the electricity. So this is a very important aspect. So because of that very high diffusion length, in spite of having poor absorptivity, you can absorb, so silicon can absorb sunlight because you just use very thick silicon. Use 200 micrometer of silicon, though it has a molar extension coefficient of absorption is very poor, but you use so much of material that ultimately light get absorbed, solar light get absorbed, and that we can do because electron can, after absorption, I'm not getting into electron hole, etc. I'm just putting one charge carrier. So electron can travel through that distance and reach the electrical complex level here. Just to give you an idea, typical other good semiconductor, I mean the word good, will have this kind of diffusion length about 1 micrometer, 2 micrometer. This about 100 times better diffusion length of silicon makes the difference. Now, when we have this, silicon is doing extraordinary, everything is fine. We have any scope beyond silicon. So in this regard, I will say that till the time of 1980s or 1990s, till this time, the development was mainly done by physicists, engineers, chemists who was probably not that significant. But then in this period of time, in this particular decade, 1980 to 1990, we could start to get solution processed semiconductor. And anything you get in solution, chemists feel that they got their own world and they can explore it. So this is precisely what has happened. And in this time, you got many new kind of semiconductors like organic electronics, quantum dot, dye-sensitized solar cell, thin films, even hybrid perovskites that I'll be talking today. The semiconducting properties discussed in this particular decade. And so it started a huge kind of not only semiconductor in general, I feel that in this decade, the chemistry of material expanded hugely, and sort of you'll see even the journals like Chemistry of Materials, which is a flagship SES journal, was launched in the same decade, and many things changed academically in this decade. And as an outcome of it, we could see changes also in our daily life. In last 20 years or so, we could see the display technology has changed completely. Even the lighting, flexible electronics, all these things that are being possible because of this discoveries that's happened here. And none of this would have been possible with silicon. Silicon cannot do those things. Not only this, there are many other opportunities. Like if you talk about optoelectronic application in infrared range, the band gap of silicon doesn't support optoelectronics in infrared range. Then X-ray detector, gamma detector, and so on. There are many other attributes of optoelectronic application you will find that cannot be done with silicon. So it is not like that we are trying to find an alternative of silicon. Instead, we are trying to see many other different materials and samples that can achieve certain properties that silicon cannot achieve. So then, when I'm going to the lab as a chemist, I need to make some new material. I need to think of a new material. How shall I start my thinking? What are the criteria of a semiconductor? So the theoreticians who are sitting here can very easily find this kind of K diagram, the electronic band structure, and one can say that okay, if you have a large kind of curvature here, then one would expect that the charge carriers, the hole or electron, will have a low effective mass and supposed to have a large carrier mobility. So one would expect a good charge transport. And if you have a direct band gap like this, one can also have a good optical transition across the band gap, so you can get light absorption, emission based properties. So this is a sort of an ideal scenario that one would like to work on when you are thinking of a material. I would expect this kind of situation to be there in my material if I'm thinking of it in the semiconductor. If I have an indirect band gap, something like silicon that I showed, it is a very good charge transport, but optical transitions are very poor. So, for example, if you are thinking of LED material, then this will probably never work efficiently when you talk about it. The other kind of thing, like here, you see it's a direct band gap, so optical transition is allowed, but the bands are so flat, it is behaving almost like a molecular state. So in this kind of situation, you'll have good light absorption, emission, etc. For example, you'll get many molecules that will be giving almost 100% photoluminescence quantum yield. But you take the same molecule, make a device, look at the electroluminescence, I'll not be surprised if you get 0% electroluminescence. That's because the charge transport will be very poor. So I need this kind of requirement, a direct band gap and high band curvature to start with to think of a new semiconductor. Now, when I enter the lab, I'm thinking of a new material. I look at a periodic table, I look at my intuitions, and I want to get those information. Whether my material will have a kind of small carrier effective mass, etc. I can get those information if I know the band structure, the EK diagram that I showed. But I'm thinking of a material that has not been prepared, that has not been synthesized. The crystal structure of that is not known. So I do not have the EK diagram. So how do I start thinking about them? If something comes to my mind, whether this will be a good semiconductor or not, how do I go ahead? So this is sort of one of the major challenge that I think if I think of a materials chemist in terms of material design, this intuition is very much required to develop a new material. And in this regard, I would say that the intuition that we follow is sort of we look for a covalent bond. Direct band gap still I cannot predict without getting the structure and the electronic band structure. But something like probably to get high band gap, a high band curvature or lesser defect, etc. Probably I need the bonds that are created has to be covalent enough. So if I have a covalent enough bond, it means that the orbitals are overlapping strongly, and that will sort of lead to this kind of high band curvature. And if I have a network of strong covalent bonds, probably creating defects will be also difficult in those kind of situations. So, in a very plain, simple word, if I try to put it, so if I have this kind of network of silicon, 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 it's a covalent network. And an electron is traveling through this kind of bond. Now, compared to this situation, on the other hand, I have an ionic situation, say sodium chloride kind of bondings are there. And if I put an electron to travel through this bond, the electron will find difficult in traveling this ionic kind of bond because of the high electronegativity of chlorine. The electron will like to reside closer to chlorine. So the movement of electron, which we will call the carrier mobility, and which will result into diffusion length, etc., will be preferred if I have a covalent bonding. So this is not a theory or nothing. This is just an intuition with which we start looking at the designing new material. To give you more confidence about this intuition, let me put this table here. Here I am just listed some of the standard or the well-performing semiconductors here. And if you look at the chemical bonding, and here is the carrier mobilities, you'll see that most of the semiconductors that are performing good, and I can calculate covalency. This is a very simple undergraduate level calculation. Calculate means I just need to need the electronegativity values of the two systems like indium and arsenium. Arsenic, what is the electronegativity difference? And from there, just a calculation, nothing serious. And you'll see that almost all the semiconductors that we know that are performing very well have a very high percentage of covalency. Now, with this sort of introduction of how we think of designing novel semiconductor, let me come and
one question with your simple. So gallium nitride and silicon carbide, all are fine, but gallium nitride, silicon carbide, of course, the covalency of gallium nitride is much less. But if I think in terms of mobility, that's actually doing much better than.
So
that's because of something else in the.
So here I will say that it will be very difficult to complete the correlation. This is just a rough kind of intuition-based thing. And after that, of course, I need to go into the more details of, say, for example, what are the kind of orbitals constituting valence band, what kind of orbital constituting conduction band. If it is a d orbital, I will expect lesser mobility compared to if it is s or p orbital. So there will be finer details, and this is just a rough thing to start with. It's not a rigorous thing, absolutely not. So
anyway, that is affected by your whole mobility. Very small.
Yes.
Gallium nitride, which is your nitrogen levels are very low. I mean, more iron.
More.
Because of that, the valence band is.
I understand.
You were saying the bands are asymmetrically large.
Yeah. In the cartoons that I showed, they are symmetric, but it's probably never the case. They will know it better than me.
So this is phonon limited mobility.
I don't really understand what you mean by phonon limited mobility.
Meaning, so is this measured in a device, or it's measured in the bulk, where the limitation is just coming from the phonons, which is at full temperature, or is it like measured in a device where you have other scattering, like surface roughness scattering, or other impurity levels or something? Because for example, in silicon you never get 100 in a MOSFET, right? This number will be like half of that.
So this assignment I gave to my student to collect this number from literature, and I believe
so I'm pretty sure these are like then phonon.
Essentially, most likely sort of single crystalline kind of things.
Even the data function must have the device temperature for both of them. The device temperature is high compared. I am guessing these are in 300 Kelvin.
These
the
are
device temperature are order of magnitude higher, so the phonon will not be that much even at 300 Kelvin. So your mobility won't be affected.
No, the problem is that this gallium nitride is for example polar material. So you have this optical phonons with this polar optical.
You mean optical phonon?
Yeah, that can kill very significantly. No, it's not like optical.
Okay, so you can think of the deeper physics here. So then I come
That's
to
the problem if you give the talk in front of it.
yes, no, but that's how I also keep learning. So then I come to the next one, that is the layered hybrid perovskite. And what I mean by that, I'll explain in this slide. So this structure again, probably half of the audience knows this structure. So this is the perovskite structure. It's so you see that say this was started with something like calcium titanate, and these are the titanium oxygen octahedra. So at the center of this octahedra there is a titanium, and then you have oxygens. And this titanium oxygen octahedra, they form the three-dimensional network, and the void that is created is occupied by this kind of calcium 2+, which we call it A side cation. B side cation is at the center here, and X is at the corners. So this kind of oxide-based perovskites are very, very well known, and they are extraordinarily good material in terms of various applications. And I'm sure almost, I believe, all of us have used this kind of oxide materials in different aspects, as a gas lighter. I'm just trying to say in a very daily life how you use many of those materials. So I'm 100% sure that all of you have used it, and these kind of materials are extraordinarily good material. However, they are not really great semiconductors. On the other hand, the similar structure is here, the cesium lead iodide, but this guy here, or this kind of lead iodide based perovskite, they are much better semiconductors. So what makes the difference from oxide to iodide? And this is again our intuition based thing can tell that if you look at their electronegativity values, titanium and oxygen, they are very different numbers, and lead and iodide, they are opposing numbers. So if you look at the covalency of this bond, because ultimately the electron has to travel through these bonds, that is through this octahedral network, is much higher when you just think of the lead and iodine bond here in the case of halide perovskite. So you see that these are the probably reason why this kind of halide perovskites are good semiconductors, but the oxides are not. And then in today's talk, I'm not really talking about this kind of perovskite. Instead, I'm talking about this kind of layered system. Now, what is this layered system? So you have this perovskite structure where you have this kind of this cesium lead iodide. This is a cesium atom filling up the void. So now, instead of cesium, you take this kind of big organic cation, so phenyl ethyl ammonium. Now, this big organic cation doesn't fit into this void size. The void size becomes smaller than the size of the ion. As a result, that these layers start going apart from each other. So this is not 1D, this is not rod, this is, you are seeing this kind of projection. So this is a 2D layer of lead iodide, and here is a 2D layer of lead iodide, and they are separated by this kind of organic molecule in between. So this is what I mean by layered hybrid perovskites. Now in this kind of system, and the properties or the things that I'm talking about is I'm talking about mainly single crystals. Big single crystals, say centimeter size and lateral dimension, thickness wise about 0.5 millimeter in this kind of system.
What's the separation between two?
This will be, say, this is something like 6.5 angstrom. I can change it. This will be something like 7, 8 angstrom, 9 angstrom, 10 angstrom in that range.
And two layers are like van der Waals or?
Yeah. So there will be van der Waals interaction. So this will be one charge neutral layer. There. So if you see that here, if you look at the conduction band minimum of this inorganic layer, here is the conduction band minimum, and then you have this organic part. This is what we call as a LUMO level. It's high up here. So if I have an electron here in the conduction band of this semiconducting layer, the lead inorganic layer, the electron will find huge barrier to go to the organic part. Likewise, the hole is also confined in this inorganic layer. It will find difficult to go to the organic. So as a result, in spite of having a big size of the crystals, the electron and holes are largely confined in this inorganic layer, which is atomically thin, which is only about 6-7 angstrom. So therefore, one can get this kind of repeating quantum well kind of structure and one can get interesting quantum confinement effect, which is very much well known when you talk about nanoscopic properties, and you can get this in a big crystals which are centimeter size, which are in centimeter centimeter dimension, thickness of millimeters. So when you talk about nanoscience, so one thing comes very prominent is quantum confinement, which is here very much, and you can tune them. It's not that this is the fixed thing. I can tune the thickness of the oil. I can tune also this barrier height, etc. I can do a lot of playing with this one, like what you do with different sizes of crystals, small size to nano size crystals, and then in nanocrystals, you get many properties coming from the interface, coming from the surface of the crystal, and here you get these interesting properties from this interface. Note that this entire crystal is nothing but a periodic arrangement of different nanoscale interfaces. So I can design those interfaces, and in fact, these are some of the things that I will be showing later when I'm talking about the molecular design of the system, and get new interesting properties.
Sorry, nice question.
Yeah.
So what's the conduction band offset and the valence band offset? The barrier heights.
So this thing can be tuned very
So
much.
what is the
Typically,
order?
it can be say 0.7 EV, 0.8 EV,
That's a lot.
1 EV. So it's a pretty high barrier.
And what about the tunneling between, because you said it's just about few angstrom average, right? So
Yeah.
what about tunneling between one layer to another layer?
Yeah, there can be some. In fact, today I'm discussing. I have not put those lines. So we published one paper. How can those kind of interaction can be there? And if I'll show a little bit of it if I put some other molecule, intercalate, etc. So I put the layers further apart from each other and how that affect the electronic properties, etc. So because of this interface, the nanoscale interface, I'm just showing you another example. So another kind of sort of confinement one can get in this kind of system, which I'm talking, I'm saying about the dielectric confinement. So you know that when the semiconductor is absorbing light, it is creating creating a hole in the valence band and electron in the conduction band. So you get an exciton. So this electron and hole, they are attracting each other via this Coulomb force, and in this Coulomb force, you see it's inversely proportional to the dielectric constant of the medium. Now, in the previous slide, we told that because of the quantum confinement, electron and hole are largely residing in the inorganic layer. In spite of the fact that they are largely residing in the electronic layer, because of very thin layer of the inorganic part, the force of lines of Coulomb force can go through both inorganic and the organic part. And then what should be the dielectric constant I should consider? Because the dielectric constant of the organic and inorganic part can be very different. And in this kind of situation, not exactly the same one, but again, it's a physics contribution that Kildish gave this kind of equation that if you talk about a 2D system and compared to a 3D system, so this is the quantum confinement effect, but you get a new factor, that is the dielectric constant. So if you change the ratio of the dielectric constant of the organic and inorganic part, you can change the exciton's binding energy of the Coulomb force in the exciton. This is something that can allow you to tune its some of the fundamental properties like excitonic binding energy in a very simple way. Like this is the inorganic layer. I'm not changing it, but I can change only the organic layer. So here, if I change the organic, if I have the organic layer that is a low dielectric constant, I get a very high excitonic binding energy, about 350 MeV. The same inorganic layer, if I just have another organic ammonium ion that is a higher dielectric constant, the excitonic binding energy is so, sort of 7-8 times tuning of excitonic binding energy is an intrinsic property. Excitonic binding energy is an intrinsic property of material, and you can change it in such a big magnitude. This is because of this nanoscale interfaces that I have between the two systems. Here.
So such a change in the binding energy, it's sort of non-local screening that's happening, right? So that should also change the oscillator strength, and you should be able to see this in the lifetime, measured lifetime.
So
you actually,
yeah, I'm not in the paper. So in fact, we probe it by a lifetime, etc. It is there. So I'm not showing those things. I'm just.
So what kind of lifetime numbers you?
So for example, in this kind of system, you'll see the lifetime of 1 nanosecond less than 1. I'm talking about fluorescence, photoluminescence lifetime. and in the other cases,
So you do a TRTL.
yeah,
Okay. And what
and
about
they
50
have
MeV?
different kind of temperatures. Go to very low
No,
temperatures.
but let's say for a given temperature.
Yeah.
So you, and then what happens to the 50 MeV number? So does lifetime actually?
Yeah, those will be kind of 7-8 times more lifetimes you'll get it. So in the lifetime data, you can see a very clear signatures. So I can also change these numbers by changing the halide ion here, chloride versus bromide. This ratio I can change, keeping the organic part constant. So the moment I play with the ratio, I can see a systematic change in the lifetime. It's very much clear. So with this, I come to the next part of the talk, that is the molecular design. And as I already told that there are interfaces, nanoscale interfaces between the inorganic and organic part. And so far I was talking mainly about how it is changing the physical properties. Here I will show that how this nanoscale interface can change the structure of the material and therefore have newer properties. So mainly I'll give you example of different non-covalent interactions like hydrogen bonding, halogen bonding, cation pi interaction, and so on. And through this interaction, I'll be able to get structural non-centrosymmetry, chirality, intercalation of molecule, water stability, those kind of things that I'll be giving you some examples. So to start with, the first example, I can think of this non-centrosymmetric semiconductor. Now, why one should think of that? So at one side, you have a very good kind of, as I mentioned, silicon, gallium arsenide, all those are very good semiconductors. They give you photovoltaics, photodetector, photocatalysis LEDs, and so on. But they have a structure that is a center of symmetry. On the other side, you have some non-centrosymmetric insulators, say barium titanate, or even different molecular crystals. They have insulating properties, and they can give ferroelectricity, chirality, nonlinear activity, etc. What if you can combine both sides? Can we have a semiconductor that is non-centrosymmetric? And if you can combine that, probably one can think of some futuristic properties like bulk photovoltaics, self-power photodetectors, spin selective optoelectronic, or even photocatalysis. You can have a LED that can emit only circularly polarized light, or a detector that can selectively absorb circularly polarized light. All this looks very fancy at this point. Perhaps there are different materials that have shown this kind of properties are possible, but their performance is still extremely poor compared to what is the requirement for real-life applications. So I see that there is a scope of developing this kind of new material, and again, we go to this kind of hybrid perovskite to meet the requirement of a non-centrosymmetric semiconductor. So what is the design hypothesis? So design hypothesis is that I have this inorganic layer here, and then I have this organic molecule. Now this is something like nitrogen here, and these are hydrogen. So the inorganic layer is connected to the organic part through this kind of hydrogen bonding interaction. These hydrogen bonds have a similar strength, so sort of there's between here there's sort of C3 rotational axis one can consider, and then the other side of the organic molecule, this is just a methyl group, carbon, hydrogen, hydrogen. So there is no interaction between this organic A and here. Now, if I replace all of the hydrogen with iodine, now when I have this, I introduce a new non-covalent interaction, that is carbon here, iodine, and iodine of the inorganic layer, lead iodide. So the moment I introduce this non-covalent interaction here, the new non-covalent interaction, I lose the rotational symmetry here, and there is a sort of non-centrosymmetric interaction that I develop. On the other hand, if I change one of the hydrogen atom with a methyl group here, something like this, there again, so instead of having a C3 rotational axis, now I do not have 3 hydrogen bonding, and I have these 2 hydrogen bonds, and you get a C3 rotational axis here. So what I'm trying to do here?
So you have here, you use 2 different kinds of molecules?
So this is one sample, this is another sample, this is a third sample.
No, A, B, C are different.
Yeah.
But in the A, let's say, you have 2 layers of the inorganic layer. In between, you have basically 2 different molecules.
No, this is the same molecule.
Same molecule.
Yeah, same molecule. 2 ends of the same molecule.
and now you are replacing, selectively one of them.
So it's
Yeah,
a chain.
it's a change of carbon. There's something like CH2 chain,
I see.
and then I'm replacing one of the. So this part is nothing but CH2
Yeah.
chain.
Right. Right.
And then I'm replacing one hydrogen here with
Okay.
iodine.
So
The chain is remaining constant.
I see. I see.
So by doing that,
So maybe I'll just
Yeah.
put a question. So do you see some uh, chirality in the vibration spectra? I don't know if you can talk of phonons here, but some chiral phonons or something do you expect to see here?
so I've not yet reached chirality. These are still not chiral, but chirality will come.
But if you break it, then it will automatically become, chirality selective, right? Because
No, not yet chiral.
no, in the B,
So we don't get with this diagram. This
I
is
see.
just a
Okay.
schematic. It's
Okay.
not a helix.
Okay.
So it's still not there. But your question still remains valid. And unfortunately, I don't have a facility, and I do not know whether anybody in India also has a facility of looking at the vibrational modes for a chiral system. You can do. I would like to talk. So, but people are doing those kind of measurements. I also need a partner to do this kind of thing. Okay, so the essentially idea is that we are playing with the symmetry of the non-covalent interaction. And but if I reduce the symmetry of the non-covalent interaction, probably it will introduce non-centrosymmetry in the inorganic part. That's the hypothesis. Now, why I need non-centrosymmetry in the inorganic part? That because the valence band maximum and conduction band minimum are constituted by this inorganic part. So if I have a non-centrosymmetry in the inorganic part, then probably I'll get its reflection in the optoelectronic properties of the system. So that's the idea, that I need to get non-centrosymmetry in the inorganic part. And that's why this hypothesis. And when I follow this hypothesis, this is my first example here. This is the organic molecule that I take. So here you can see that this is the ammonium group and this is the iodine here. And so this first example that I'm taking, this is nothing but this case B here. And when I did this experiment, this is the hybrid perovskite structure. This is not a schematic. These are all single crystal XRD that I'm presenting here. So in this structure, you'll see that there is a center of symmetry is there. So these are lead, iodine, and here are the organic part. Many of the things are truncated. This is the structure, and you get the inversion symmetry here. You don't get kind of non-center symmetry. Then what I do is that I replace one of the hydrogen atom here with a methyl group. That is, I go to O. So that means I go to this case C. And when I do that, you see that the inversion symmetry is no longer there. I got a non-crystal that doesn't have inversion symmetry. If you look at this, this is the lead and this is iodine. So if you draw a line here between the red spheres, you'll see that iodine is little bit off center. It is shifted that side. So you get a sort of dipole moment in this direction, and this keeps on adding. So all the dipole moments are in the same direction. So you get a polar structure, and the space group that we get here, it falls into a ferroelectric space group. So you get a non-centrosymmetric polar structure by substituting one of the hydrogen atom with the methyl group. So it looks like the hypothesis that I showed in the previous slide is at least applicable in these two examples, but two examples are not enough. So we made a library of samples. We took various kind of organic molecule, and
So
yeah.
of course, the way you have designed, it will be a non-central symmetry. But can you make sure it will be always polar? And the polar group is a subgroup of your non-central symmetry. Not always it will be. And of course, electricity and further smaller.
So that is probably not possible to say directly, but we essentially look at the space group and whether this space
Once
group
you have
falls into.
created.
Yeah. So then we extended this idea to different lead-based, Bismuth-based 2D or layered perovskite or one-dimensional perovskite, etc. And it looks like the hypothesis that replacing hydrogen atom with something like methyl or iodine, that is essentially that replacement introduces dissimilarity in the non-covalent interaction, and that lead to non-centrosymmetric hybrid structure. So we could see it for a 7-8 such system, which gave us more confidence that probably the method is applicable to multiple systems.
And also have a transition.
We have not tried, but it should. I don't see any reason why it should not. Yeah, these are for all this material made single crystals, and you see the space group has been mentioned in all those cases. We look at the crystal structure in great details for all. So another proof of non-centrosymmetry is you can get nonlinear optical properties. So I gave the sample to my collaborator Pankaj Mandal from IISER Pune. So he and his student, for example, when they shine this 15-18 nanometer light, one of the non-centrosymmetric crystal, they get this second harmonic generation, the 790 nanometer, which is here. And if they tune the incident wavelength, incident photon wavelength, accordingly, the SHG signal also tunes, and you can see the different wavelength. And incidentally, this is not because of non-centrosymmetry, but incidentally, this sample also shows third harmonic generation. So it's third harmonic generation has nothing to do with centrosymmetry or non-centrosymmetry. Both kind of sample can show third. So it shows third harmonic generation also. So it is one incident wavelength, you can get two nonlinear optical output, and they can be very across the range with the electromagnetic spectrum.
So what's the band gap of this optical band gap?
So this optical band gap will be somewhere here, around 500 something.
I mean, to make sure that the SHG that you are
SHG
getting
is outside, but
outside,
THG
yeah.
is inside.
Yeah, okay, yeah.
So
No, because you will
THG.
have this, two photon luminescence, also.
But two photon luminescence will also respond to the band gap. It will not get tunable with the wavelength of the incident light.
That's true.
So there is absolutely no doubt about. So when I'm exciting at 15-18 nanometers, it's very far from the band gap. So there is no doubt on that.
The kind of algorithm,
It's say, for example, when you talk about upconversion, if I understand the language, we talk about that we are shining with wavelength light, like what you was mentioning, say something like two photon emission has happened, and then it is emitted light, photoluminescence is come at a higher energy. It is not there.
and those are pretty cool. Those are 527 nanometer.
This is third harmonic generation. If you look at the nonlinear optical properties, so they will see things like second harmonic generation, third harmonic generation, multiple harmonic generations that are very much there. So if you shine with lambda, you'll get lambda by 2, lambda by 3. If the sample has that nonlinear kind of strong cross-section for this nonlinear.
So you said you do some single crystal.
Yeah.
So any entanglement between the output?
So we could see, there are some PMAs that we have done, and we could see like when you have the different direction of the incident light, etc. And I go into the details. We'll see here in the crystal structure there are two directions we could see the polarity, and we could see similar signatures, but we are not that confident, so we are not naming those things very much. We could see some selectivity on this kind of thing based on the polarization direction of the line.
Maybe you should do a Fourier mixing type of experiment.
We should do.
Yeah.
Because what I'm trying to
Yeah,
do is beyond my
interesting.
capability at this point.
No, the systems are very
Yeah.
That's why I saved you. You motivate a lot of people.
So I'll be very happy if you come up with your solution ideas and doing some any collaboration. Very happy to do so. If you, for me to make these samples are not very difficult. If you just want to try something, I can just give you some samples.
So how stable are this like?
This is stable. No problem.
And
For months they are stable.
you can go to low temperature. No problem.
Yeah, many of these things.
So no outgassing or something.
No. Because the organic molecules are pretty big enough, so outgassing is not there. So for most of the sample, we do low temperature photoluminescence down to 5 Kelvin, etc. So then another thing that happened, I showed you the library of molecules that we have synthesized. One sample decided to become a chiral system. We have not done anything. So interesting part is that the ingredient is achiral. The molecular ingredient is achiral, but when you got the hybrid crystal, the crystal is forming in a chiral space group. And if we look at their absorption, this is the absorption data and this is the CD data. You'll see that in the CD data corresponding to the absorption, we see some signature. But then we don't have much control of it. To have a better control of it, one can always try to start with chiral organic ligand, and that's what we do here. So these are not our synthesis. People have made it earlier. We have followed their procedure. So you can choose whether you want to have R or S enantiomers of these organic molecules, and then if you make a hybrid structure, your hybrid structure will have both this R or S enantiomers. And what we did is we measured that single crystal and tried to see that how the chirality has been transferred from or induced by the organic part to the inorganic part. And if you look at this is the single crystal XRD data only for the inorganic part. So racemic means it's a 50-50 mixture of both R and S. When you have this, we don't.
So you can selectively have R or S.
So we commercially buy it. Organic chemistry people, they can selectively synthesize it. We are not that good, so we just buy it. So then we get the centrosymmetric system here, and you can see the lead, for example, lead, iodine, lead bond angles, etc. are same, and you get a centrosymmetric structure. But either for R or for S, you see the lead, iodine, lead bond angles, they are different, and the centrosymmetry is lost, and they are now in a different kind of space. And this again could have been done because of this nanoscale interface. What we think is that the hydrogen bonding interaction that can induce non-centrosymmetry in the inorganic part of the system based on what is the choice of our organic molecular ion. In this kind of system, you can have a more clear CD data, more controlled way. So you can see for a racemic, so this is the absorption data, and I'm talking here the absorption that is because of the excitonic transition, which is coming from the inorganic part. And for that inorganic part, we are seeing the CD signal is still. So essentially what I'm trying to say is that it is not the CD from the organic part. The organic part could have induced chirality in the inorganic part, which is getting reflected in their optical properties. So for the racemic structure, you see there is nothing. For the R and S, we see almost a mirror image kind of data in the same.
What exactly is the structural changes with the inorganic?
So you see sort of, you can, I'm not really confident, so I don't talk about this helicity and don't understand it, but you can see some this kind of structure which probably I need to understand a bit more clearly. Space group wise, they're same. So,
Yeah.
Space group wise, they're same, but they're probably orientation wise, there's some differences. So some people talk about helicity, but I'm not yet confident enough to claim that.
So convention about this dash process, sorry, it's like out of plane, so cross and
This one?
coming out and going into the plane.
This
Yeah, those.
probably not really. My student made it. I don't think it has been enough thought has been put.
And so I think naive, but in the next slide. So what do you mean by CD, BD degrees or something? So what are you exactly measuring?
So say I'm putting right circularly polarized light and left circularly polarized light. The crystal that the light is getting sent of say you have the R is going in
So
one.
are you measuring transmission or
Transmission?
Transmission you're measuring, and there is an angle. So basically, it's becoming the elliptically polarized light.
Yes, exactly. So it's becoming elliptically polarized light. And since chirality obviously also have a non-centrosymmetry, so one can think of doing again. Pankaj Mandal did some SHG measurements and get the SHG signal. It's nothing surprising. So after that, maybe I'll just give this example. One example of again, I get impressed with this molecular design. So I'm just giving an example without going much into details of it. So typically, what we have a crystal, a semiconductor fine. Now here we get a unique kind of situation that this organic part that we have, they are not very rigid, they are sort of flexible. So you can it is possible to insert certain molecule there if you can think properly. So this is an example. Again, it is not done by us. We followed previous procedure and we did this measurement for different purpose. You were telling earlier about the coupling between the inorganic layers, etc. So this paper deals with that precisely. I'm not going to do this, but just I'm giving you this example here of molecular intercalation. So now what you can do, you can intercalate. So these are phenylethyl benzene ring. These rings have electron rich, and then you have another ring that is electron deficient. They can stack and they can form single crystals. This is a single crystal structure, very solid structure you can get. Now, when you do this intercalation, you can look at this photoluminescent data, the photoluminescent property significantly. You can feel the electronic property. Another very weak kind of interaction here. Here, I took another different molecule, iodine. I have this crystal, and just I put the crystal in the iodine vapor. If I put it in the iodine vapor, some of the iodine gets into it, and this interaction, however, is not very strong. So, if you remove the crystal from the iodine vapor, the iodine again comes out of this. So, reversible intercalation, etc. one can do. Here again, you can see that this is the photoluminescence, the blue line or green line, whatever it is. This is the photoluminescence of the before intercalation, and after intercalation, you see this peak got completely vanished. Actually, this peak came because of the interaction between two layers, which got vanished. That's our proof that we are talking about this one for this intercalation. Same here is also this lower energy peak is coming from the interaction, which got vanished into the intercalation. So this kind of
This emission, right?
yeah, yeah.
It's interesting that your higher energy peak is of higher intensity. So, I mean, but you are doing emission, so it will try to kind of go to the lower energy, right? So,
Yeah. True. So
a huge difference in oscillator strength, or
this is something very surprising when we started with. So first of all, in a single crystal at a room temperature, these are all single crystal measurements. In a single crystal at room temperature, one would not expect to see two excitonic emission. This is something very surprising. And when you look at it very carefully, what we see is that this kind of interactions are coming mainly from the edges of the crystal. It is also specially resolved thing. So the occurrence, it's not a defect, it's like it is there systematically. It's not only one defect in the field, but sort of edge effect, but this edge are there. So it is not about higher oscillator strength, but occurrence of those states are less. So if you take a film out of it, then you'll see that this you'll not see this peak. It will be going like a tail kind of this. In a single crystal, when you have a large crystal, as you mentioned that it can transfer its energy or self-absorption, because of those prospects, in spite of lower occurrence of this state, the state becomes more intense. So, essentially, the message that I wanted to give from this slide is that here again there is a unique opportunity with this method, that enormous amount of this kind of molecular intercalation, and something that, in my opinion, has not been studied yet very aggressively. So one can think of the different sensing of molecules, or you can think of putting a molecule with a different functionality, say chiral one, say magnetic one, and one can try to play with this design principle if we have the right idea here. So after this, so far I was talking about non-centrosymmetry, chirality, molecular intercalation. So essentially designing structure property relationship, and we are tuning those structure property relationship based on the nanoscale interface between the organic and inorganic part. Now then, the another problem in this field is the water stability. So I mentioned that lead iodide is covalent. Like when I talk about cesium lead iodide. So lead iodide is not really a problem. If you just make a PbI2, in water they are reasonably stable. It's not a problem. The problem is the third part, that is the cesium part that is there. So it is an ionic interaction between cesium and lead iodide. And that ionic interactions get disturbed the moment you put water. It's like a sodium chloride salt, it just dissociates immediately. So that's one of the biggest challenges in this field is the water instability of this kind of system. Now, compared to like 3D perovskite, like cesium lead iodide, etc., if you put the organic ones, the 2D perovskite, the water stability improves simply because there is a hydrophobic chain in this organic molecule. But even then, this improve is not good enough. You take this 2D system, put it inside a beaker of water, immediately they will dissociate. So we are thinking that can we improve the stability, and since we identified that the A side cation, this organic part is the trouble-making one, we thought to introduce some molecular interaction between themselves. If the organic molecules themselves interact strongly, in long range, probably they can counter their interaction with the water. So with that hypothesis or that idea, when we started thinking, my student Tariq came out with this molecule. So this is the organic molecule, both sides it has a nitrogen atom, and then they can be arranged in a crystal in a way that one of the ring here, the pi electron ring, is exactly on top of the NH plus ring of the other one. So one can think of establishing this kind of cation pi interaction in this system. So with this idea, he made the crystal. This is the hybrid perovskite crystal that he got, and this is the crystal structure. And in the crystal structure, if we look at the organic part, you could see that this is the nitrogen, this is the pi ring. They are indeed arranged in a way, and the cation pi interactions are there. However, unfortunately, the inorganic part did no longer remain a 2D perovskite that we wanted to be. Instead, it became a sort of 1D structure network, and even the one of the core criterion of the perovskite structure is the corner shear octahedra, which is lost here. So yes, we got what is the kind of the structural cation pi interaction, but somehow the organic part did not obey our wish, and it acted in its own way. Nevertheless, since we made the material, we looked at the water stability. The water stability is superb. You take this crystal, put it under water, day 1, 3 months, 6 months, and we know that they are stable more than years now, and absolutely stable, no problem. They also emit light. So this is the broad light emission that comes out, and it happens to be a white light. So just a toy experiment that we take a UV chip and coat it with something and get a white light. Helps go through the review process. So just made it, nothing serious here. Also, this sample again, Pankaj Mandal did some nonlinear optical properties. So we ended up with a system. This is a hybrid lead halide system, though not perovskite. It is optically active, but in this kind of system, by design, the charge transport is expected to be very poor because I have a 1D network, and between the 1D network, I have the insulating organic molecules. So then we thought to improve this situation a bit better. So this is the situation that I presented just now. This is the organic molecule, and if I consider this is the inorganic part, and this is the organic linker between the inorganic. So we thought that if we can introduce a double bond here, so from here we are going to the next sample that is just having this double bond. So if I have a double bond here, then there is, it establishes a pi conjugation through the molecule, and hopefully that will increase the electrical transport between the two. And with this idea, then we made the next sample. So this is the sample without pi conjugation, and this is the sample after pi conjugation. And if you just look at the band gap, the band gap is, there's a big change in the band gap. The color of the sample changed. This sample with pi conjugation, the yellow colored one, this is also very much stable. So water stability wise, it retained its property after the pi conjugation also. And maybe I'll go first with this. So our collaborator Shudip, he did he calculated this DOS for this system, and he could see that after pi conjugation, this is without pi conjugation and this after pi conjugation, you could see a new peak the conduction band, which explained the reduction of band gap, etc. that we discussed. And then another collaborator, Atikur from IISER Pune, he did this transport measurement, and so he just put the single crystal and made the contact. And so you can see that in dark, this is the response, and when you shine light with 405 nanometer, you get some photocurrent. And this, then the same thing, he did it at different wavelength. You could see that the onset of photocurrent at the wavelength matches with the optical absorption data, suggesting that the photocurrent that we are seeing is coming from the sample. So on the other hand, the red one is without pi conjugation. This doesn't show any photocurrent. So something like we are getting from 0 to a non-zero number. Numbers are still very poor, but something you get from 0 to a non-zero number. So this, I come to the conclusion of this discussion. So what I try to tell is that we can have this kind of big single crystal. Most of the data that I've shown here today, whether optical or otherwise, these are coming from one single crystal. So when I have this big kind of single crystal, within this single crystal, I have this kind of nanoscale interfaces. The entire crystal is nothing but nanoscale interface between organic and inorganic. And if I can design those nanoscale interface cleverly, we can introduce many new properties. So it is like composition of organic sublattice often is ignored because, as I told earlier, the valence band maximum and conduction minimum are contributed by this inorganic part. So inorganic part determines the property, and this organic part is often considered just this to stabilize the structure, to have the structure, hybrid structure. But if we can play with this organic sublattice carefully, then it can introduce newer property and newer structure to the inorganic sublattice, and essentially one can get the combined property of both organic and inorganic sublattice, even though the optoelectronic property is mainly determined by the inorganic. And so that's what this kind of thought process I've written in one of the perspectives. This is the title of that perspective, the plenty of room at the interface of hybrid metabolite perovskite single crystal. If you're interested, you can go ahead and look at it. And these are the guys who have done the work. This is an old photograph, and I put the old photograph purposefully because the work that has been done today is mainly by these two guys. Both of them have completed their PhD and they are now doing postdoc abroad. So the present photograph of the group, they are not there, but the work that I am presenting are from these guys. And also after them, Parikshit here has contributed quite a bit. Presently doing the fourth year of his PhD, and he's contributing in this direction. Funding came from IISER Pune. Thank you all for your time.
Thank you everyone for this very engaging and informative talk on the next slide. So we can take some questions, maybe from other group.
Thank you. It was wonderful to listen to you and learn about this perovskites. So I was just wondering, at the end you showed the molecule where you have helium and iron, but is it done in the like aliphatic molecules? For example, he was always showing about the ammonium cations only one side, but not on the both sides. Is it done in the aliphatic? How does that way?
So some of the examples I have not mentioned very clearly. There are,
For example, slide number 15.
yeah. So for example, here this is a aliphatic ion. This is a butyl ammonium. It's just the butyl group. So here this is at one side representation-wise ammonium group, but then you can have this kind of aliphatic ions also both sides having ammonium group. So it's possible, but this kind of what I was trying to say here is the cation pi interaction that I cannot get, of course, with the aliphatic picture.
So does it have to have some conjugation into it? Or
No, no. It's in fact most of the example that I showed, it doesn't have conjugation. So conjugation, we wanted to add it later on to have some kind of electrical communication between the inorganic.
Okay, but it's not essential.
No, it is not.
And the second question is about like he was always showing around. In the next slide, the example is much better. The one with chlorine, yeah, the hexafluorobenzene. And this one. Every example you show, it's a crystalline one. You synthesize the material and then it's implement here. Is it possible to exchange it somehow? For example, one of these, not necessarily the hexafluoro, but the organic cations, for example, the bigger one with the smaller one, or the linear one with the smaller lengthwise. Is it at all possible by any interactions? Or is it done anything?
I'd say that we have made some half-hearted tries. When we made those tries, it's like what we tried is that we have a, for example, a chiral system and just soak it into a chiral molecule, whether any kind of exchange happens or not. We could not get any positive result, but nevertheless, I should not tell that it is not possible. And we have not also tried it enough. It might be possible. So that if it works, then it also helps you to open up your box of molecules.
Box actually, yeah.
Any more questions?
I have one small technical question. So in your slide of third hormone inhibition, second hormone, the intensity is more or less equal for both.
No,
Maybe
these are normalized.
normalized.
Yeah. more than 1 meter.
What is conjugated ligand? Can we get right now the electroluminescence?
Electroluminescence, as I told, most of the data that I've showed in a single crystal. So we have not made the film, we have not made the device. We only to make the device to see the film. So in principle, yes, but we have not made.
When you are referee, you can also
Maybe then he can see.
So the idea is like that. If we have more mobility of charges, then we can be
True. Very much, but yeah. So right now we are sort of learning little bit of trying to make. We are taking just a small baby step to make the device in the lab. Let's see.
maybe the reason properties are governed by both components and we don't know that change. You know, sometimes it's like ionic particles much more what we don't have problem.
I don't know if you're talking about the electroluminescence part, there it's not coming from a one material. There are a lot of interfaces we have to make, so it's altogether a different device structure. So that interface, how easily a charge is getting transferred from one interface to another interface, etc.
So just a question that has anyone tried with any other halide, like apart from iodide?
So we ourselves have also studied with chloride, bromide. So these three are very regularly done: chloride, bromide, iodide. But in general, we try to stick more to iodide because of the first reason that I told I want a covalence and the semiconducting property. The more I go from iodide to bromide to chloride, the electronegativity increases, the semiconducting property decreases.
It is between the iodine and iodine. So
No.
Oh,
So
between
lead
the-
and iodine,
lead.
lead and halide. So even you'll see that the solar cell, etc., that you'll see, it's mainly the iodide part. Little bit of bromine is fine.
Okay.
The moment you bring in chlorine, you'll get a very wide band gap and it start being more like an insulator.
Right.
Yes.
Any more question? Okay. Any more question?
I already asked about it.
Thanks for